Okay, guys, today we're going to be doing a super math intensive lesson. We're going to go through 3 different nodal analysis problems that I made up, and I made them slightly difficult. So hopefully, well, I think they're okay. I think it's a good introduction to using our method that we learned last time, the nodal analysis. And these are going to be super fun, especially once you get the hang of it. So please rewatch this video multiple times if you can. It's going to be a pretty long video. I can already see it because I'm going to go through every single step, all the algebra that goes with it, all the times that I'm going to use a calculator, because I've noticed that a lot of the times, like during class, the professor will just do the problem, they'll get through the circuit part, but then they will completely skip over the algebra parts and like parts that people may have forgotten. Yes, you may probably should know how to do it, but I think the important thing right now is to build up confidence so that you can actually enjoy doing these circuit problems. So the first thing that we're going to do is solve for Vs. Okay, well, that's the idea of this problem. And Vs is this battery right here. So we need to figure that out. And earlier, if you caught that, I kind of deleted Vs right here because this little circuits part of this is that everything past the battery right here is going to be Vs. Everything here is going to be something else. Okay, everything here is going to be something else. So let's go ahead and perform our nodal analysis algorithm. So step 1 has actually already been done for you. We've determined ground and we've determined the nodes and stuff like that. So our step 1 is just going to start with straight up KCL. And if you haven't watched the last video on nodal analysis, highly recommend you watch it. Unless you're looking for practice problems and you already know how to do all this stuff, then I am just going to solve it. Okay, so we're going to do node 1 first, and we're going to look at node 1, which is this guy right here. And node 1 has currents going this way, and this way. So we're going to take into account each one of those. So first we're going to do V1 minus V2. We're going to do this node first. That one first. We're going to do this one a second and this one third. V1 minus V2 over 1 ohm. Okay. Plus V1 minus 0, and remember, ground is still a node, so we're going to go ahead and put the voltage there, and we called it 0, over 2 plus V1 minus Vs over 1 equals 0. And then we are going to multiply across, and I'm going to choose 2 because it gets rid of this denominator, because we don't want to work with fractions. Fractions are ugly. So 2v1 minus v2 equals plus v1 plus 2v1 minus vs equals 0. And then we get 2v1 minus 2v2 plus v1 plus 2v1 minus 2vs equals 0. In some portions of this, I am going to speed up the video. I won't be talking. I just want to show you guys the mechanical steps, because I was talking to a lot of my friends, and a lot of the times they just feel like the professor just teleports to an answer. So I'm just going to have it sped up so that you can look through it. No talking, whatever. But yeah. But for now, because this is the first problem, I'll walk through each one of my steps. So 2v1, so we've got the v1s combined like terms. So we got 5v1 minus, and then we got these like terms, for Vs, like so. Actually, I just already made a mistake, and this is the reason why you should look. V2, Vs, those guys don't combine. Oops. And that is our first nodal equation. Let's do node 2. So let's look at node 2 now. I'll do this one in blue. We've got node 2 right here. We've got a current going this way, and this way. This one can be current 1, 2, and 3 with respects to this node. So let's go ahead and do that. So we've got node 2. The starting point is voltage at node 2. And we're going to do branch 1 first. And now notice something here. Notice that we are going to the back of this battery. Okay, so then that means we don't know what Vs is. So we're going to have to take the negative side of this battery, because that is the only reason, that's the only way to maintain our coordinate system that we had chosen. So we are going to do V2 minus negative Vs over 2 plus V2, and then we're going to go back here. We've got V1 next. V1 minus V1 over 1, I believe. And then plus, now check this out. The current here is already defined because we have a current source. Okay, so we just simply put this in, because remember, what is nodal analysis? Nodal analysis is just the sum of the currents, right? The currents which are in terms of the voltage. So we already have a guy that's in amps or in current, so we can just put him down here, equals 0. And then once again, we're going to do the common denominator, and we're going to multiply everything by 2. So V2 plus Vs plus 2V2 minus V1 plus 2 equals 0. We get V2 plus Vs plus 2V2 minus 2V1 plus 2 equals 0. Minus 2V1 plus 3V2 plus Vs equals negative 2. And this is our second nodal equation, okay? And I would highly recommend underlining them or rewriting them somewhere else. Let me actually do that so that I don't get confused again. Okay, now our last nodal equation, which is going to actually be Vs itself, right? So we have Vs, and we don't need to count this branch right here, because this is the voltage at that point, right? The voltage is being produced here. Okay, so the voltage is just right here. So all we have to do is take into account the current this way and the current that way. Okay, and we also have a current accounted for up here. So node 3, we're going to start with Vs, and it's going to be Vs minus V1 first, I believe. Yep, V1 over, what was it, 1 ohm, plus Vs over, I forgot what it was, 3, equals 0. Once again, do your algebra stuff, and you are left with negative 3V1 plus 4Vs equals 0, third. Now, notice here we have 3 unknowns and 3 equations, so we're going to go ahead and put this into a matrix. So step 2 is to solve this. Now, notice here I'm going to actually line this up Normally I'm not going to do this, but for the sake of this intro video, I'm going to do that. So 0v2, there is 0 v2s right here. And now we're going to plug it into a matrix. I hope that you guys have taken some form of linear algebra or know how to do some kind of matrix, because I'm going to be using matrices in this. I will not be solving these by hand because that is a waste of your time, and you should not be either. You're going to pull out your calculator, your handy dandy TI Inspires or TI-84, whatever you have, and solve these problems out. So the reason why I'm putting in a matrix, as explained in the last video, is that it just makes things look better. So V1, V2, and Vs. Remember to make sure that you have each of the equations that you want, like this, equation 1, equation 2, equation 3, and then it has to equal the correct, like the corresponding y value, okay? And yeah, this is not a linear algebra class, this is circuit, so I'm not going to explain all of that. Okay, now we're going to plug it into the calculator. And thankfully, our answers are a little bit nice, and we are going to get V1 equals -1/2, V2 equals -7/8, V3 equals -3/8, and each one of them are in volts. And what did the problem ask? It asked for Vs, so we are going to only report Vs. Vs is equal to -3/8 volts, or for the decimal people, I don't know what your professor likes, but I'll write down the decimal as well, -0.375 volts. And this is the answer. Now, what if we want to check it? So once again, for the sake of these videos, I'm gonna check these so that you have a reference. Eventually, I probably won't, depending on how long these videos actually get. I don't want them to be too long, and I don't want to waste your time either, but we're gonna go ahead and do a check. So a check is, as said in the previous video, all we're going to do is just plug in these values into our KCL equations. And I would highly recommend using these KCL equations, because these KCL equations might be, like the simplified ones, might be right or might be wrong relative to this, because maybe you did some algebra error. So might as well go straight to the source, because this is the actual circuitry. This is the actual circuit analysis, this portion right here. Not this. This is algebra. Okay? So let's go ahead and do that. Our first nodal equation is, this guy right here, and we're just going to simply plug and chug. So I'm going to speed up the video here, and then we'll calculate them. Okay, this is what I ended up getting. I could have possibly made a mistake, so let's go ahead and check it right now. Okay, it looks like we're all right. Everything is 0. So that's one of the practice problems that we're doing today. Okay, here's the next problem, guys. So it says find Vs, this one, such that the 25 kilo ohm resistor dissipates 100 milliwatts. Okay, so in this one, we actually have to find we have the power here, okay? So power here is 100 milliwatts. And so from here, we're actually given some initial conditions, okay? So step 1 is to figure out what those are and apply them to nodal analysis to find this Vs right here, okay? So the most obvious thing is to find current from power given, right? Because we know that P equals I squared R. And so we're going to get 100 times 10 to the -3 equals I squared times 25 times 10 to the 3. And we're going to get I equals plus or minus, and let me type my calculator out, And we get plus or minus 0.002 amps, or I equals plus or minus 2 milliamps. Now, there's nothing from stopping you from doing this, v squared over r, but you have to ask yourself the question, is this going to be helpful for me in this case? There is another method that we are going to learn that's almost, well, just as powerful as nodal analysis, called loop analysis, but we're not going to do that yet. So this is just going to be a case-by-case basis as to discerning, where to get which equation to use. So in this case, I chose I because you'll be able to see later that it's simpler. Now, you may be wondering about this plus or minus. So this is literally just saying that we have one current going this way and we have another current going that way. And we can decide which one is the minus and which one is the positive. I'm going to call the positive as going this way, plus 2 milliamps. And I'm going to call the negative as this way, minus 2 milliamps. And the reason why is because we are given a ground in this case. So we're not we don't have to treat this as a node right now because we only have two unknowns and we have two nodes that we can do this from. So we don't need a third one. And it's just more convenient by my convention to call this minus 2 milliamps because it's just going into the node. So I just go ahead and put minus 2. And this one as plus 2 milliamps because it's going out of the node. So it's just more convenient. Okay? All for convenience sake. So the next step is we're going to do a nodal analysis. But let's do the plus 2 milliamp current first. Okay, so then that means this also means we're going to have two possible answers for Vs, because we have two possible directions, because it didn't give us explicitly if it was like if it was a positive power or not, if it was a negative power. So we have two possibilities. So let's go ahead and build our nodal equations. So node 1 is going to be at voltage 1 right here, and node 2 is going to be right here. We're going to choose this one because we quote unquote don't know it. We actually do, because this battery right here is forcing a 5 voltage node right here. Okay, so node 1 is going to be V1, and we're going to do this branch first, this branch next, this branch, and then finally this one last, which is already predefined for us. So we're going to do V1 minus negative Vs over 1K minus negative Vs over 1K, or 1 times 10 to, I typically like putting 1K because it's easier than putting times 10 to the 3. Just remember that, okay? Plus V1 minus 5 over 1K plus V1 minus 0. I'm just going to put V1 over 2K. And since we're starting with the plus 2 first, we're going to do plus 2 here. We're going to simplify this. Okay, and we get 5V1 plus 2Vs equals 6. Now let's do node 2. And remember, we're starting at 5 volts this time, because that's what this node is, and we have only 2 branches to look from. So we have, I believe it's 5 minus Vs over 2K plus 5 minus V1 over 1K. Make sure to check that just in case. Yep, 2K and 1K. So we're going to get this. And our final result is 2v1 plus vs equals 15. Okay? Now we're going to take these two equations, we're going to put them into a matrix, and then we're going to solve them. And after calculating in the calculator, I actually already did this, so we're going to get V1 and Vs equals, and we're going to get V1 to be negative 24 volts, and Vs to be 63. Okay, now this is what we're looking for. Now we're not done yet. We have to do step 3, and that is nodal analysis with negative 2 amps this time, milliamps. Okay, so same thing, N1, and now I want you to notice something here. It is the exact same thing. It's the exact same nodal equation, except this guy right here is now a minus. Okay, so we're going to go ahead and simplify it out. In fact, we can just look at this right here and say, look, 4 is the only thing that is going to change. It's going to become negative 4, so we can just literally copy paste this whole thing. Now I'm being lazy. If you're doing this for the first time, please redo the whole thing, okay? It'll help you out. Now we're going to put it back together, and this time it's going to be plus 14. Okay, and the cool thing is the thing that is the other node is not dependent on that current source, so we can just directly copy and paste all of this, and I can show you that right here. If we have N2, it's still going down to Vs, and we have N2 going down to V1, and then that's it. We are not affected by this right here. So we're going to go ahead and put these guys into a matrix. Five and 2, 2 and 1, V1 and Vs equals 14 and 15. And once again, we've already calculated these, so V1 equals negative 16 volts, and Vs equals 47. Now you're welcome to check it. We'll go ahead and check it right now. So we're going to plug into this equation first, this one right here, the one with the plus 2 milliamps, and we are going to get, now if we check the other one, now we are going to plug in this negative 16 and 47. Well, actually, just for completeness, we can go ahead and plug in this one as well and get 0. Okay, now we are going to plug in negative 16 and 47 into this equation, and we get 0. Okay, that's problem number 2. All right, guys, last one. This one's a little bit of a long one, but let's just get to it. So, we're going to go ahead and start with the nodal analysis. All right, so let's look at the first node, node 1. So node 1 is with V1 right here. Now notice something very important. We can draw a nodal equation here, but we can make a nice simplification. So the ground seems to be directly connected to V1. And remember, at a node, it shares all the same voltage. So that means that V1 is simply 0 volts. Okay. Now node 2. Node 2 is right here. Now we have to do a nodal analysis here. So we're going to do V2 minus, and we're just going to get that 0 out of the way already, V2 minus 0 over 1 ohm plus, hopefully you guys can't hear the lawnmower outside, but yeah, anyway, V2 minus V3 over 10 plus V2 minus V4 over 4 equals 0. I'm going to go ahead and simplify that out. Multiply by 10. Actually, let's multiply by 20. Okay, so we get 27V2 minus 2V3 minus 5V4. Now N3. So it seems like we have right here node 3. And we are going to go from V3 to V4, V3 to V2, and V3 to the 3-volt battery. So let's go ahead and do V3 minus 3 over 2 plus V3 minus V2 over 10, I believe. Yep. And then V3 minus V4 over 2 equals 0. Going to multiply by 10, so 5V3 minus 3 plus V3 minus V2 plus 5V3 minus V4 equals 0. And we get 5V3 minus 15 plus V3 minus V2 plus 5V3 minus 5V4 equals 0. And we get negative V2 plus 11V3 minus 5V4 equals 15. Last one. We have V4, and we've got this way, and inwards. So we're going to do V4 minus V2 over 4 plus V4 minus V3 over 2 minus 2 equals 0. Multiply by 4. And that's our last nodal equation. So let's go ahead and group our nodal equations. And notice how we got rid of V1 because it's 0. So it doesn't have to be a 4-variable system of equations. So it just makes that computation that much more easy. And then we are going to get V2 equals 1.407, V3 equals 4.185, and V4 equals 5.925, and finally V1 is equal to 0 volts. And this is the answer right here. For the first part, now we actually have to find all the currents in each branch. Now, what I like to do here is go to each node, right? Go to each node's nodal equation and basically label them. So we're gonna go here and we're gonna call this one I1, right? And then we're gonna go up here and we're gonna say from this node we have I1, right? Or sorry, this is node 2. So from this node right here, we have I1, and I1 is going from V2 to 0, which is this way, okay? So we're going to call that I1. Now this, we're going to call this I2, and that's going up this way to 10 ohms. So we're going to call that I2. This one we're going to call I3, V2 to V4. And then we're going to move over here, and we're going to call this one I4. So that was V3 to 3. Actually, in my notes, I'm just going to go ahead and call this one I4 so that we can be consistent. Okay, so V3 to V4. So this is I3. I4, sorry. Now this one, V3 to V2. V3 to V2. We've already named it right here. So we don't need to name it again. So we can just ignore this one. We can use it later to check with this one right here, and they should be the same. Okay? So let's go ahead, and I'm going to write this node in a different color. I5. Now, is this one labeled yet? No, it's not. And then finally, let's see, V4 to V2. It's already labeled. I forgot to label this. And V4 to V3. V4 to V3, that is already labeled. And that seems to be it. So now we are going to go ahead and solve for them. That's what we get for I1, I2, I3, I4, and I5. And so some of these are negative, okay? So when it's negative, then that means that the polarity that we had given it in this case from, that is actually the opposite. So 3/8 through 3/8 over 27, which is I1. That means that it is actually going in this direction, okay? Now, I2 is negative. So then that means instead of going up, it's actually going down. I2. Same with I3. It's actually going to the right. And then I4 is going to the right. I4. And I5 is continuing in its path this way. Now, we are still missing one branch, and it's this one right here. This branch right here. So this one, you can solve for this using Ohm's law, okay? And we're going to call this one I6. So basically, we're going to use Ohm's law, and we're going to say that the current is going out of V1, okay? And so we're going to call that current I6, and we're going to say that we start from 0 and we go to 2, and we divide it by 8, and we get -1/4 amps. And I'm going to put amps on all of these. And this is all, these are all the answers. So yeah, that one was a little long, and you can indeed check all of this. I checked this before, and the total current going in and out of this specific node is actually 9/4. So minus 9/4 is 0, right? And I would encourage you to check the currents, into each node and determine that they are 0. And yeah, that's it. Hopefully you guys learned something in doing these problems. Even I get a little bit confused sometimes when doing them, so I would highly recommend you redoing these problems and checking them out. They're gonna show up a lot, and the concept of nodal analysis is very important in circuit analysis.